First, I would like to have a quick recap about linker relocations, then a few words about relaxations, and I would like to present the ZCMT. The bulk of the presentation is about ZCMT and ZCMI. Then at last, I would like to put the thing in context of LTO and Volt. So let's quickly start with relocations. In this example, we can see a very simple example. There's a global variable, and whenever the compiler generates the object file, actually it so for loading the address of the global variable is basically done by two instructions: the load upper immediate and the load word instructions. And what's interesting to see here is that the value of the operands are basically dummy 0 values. The reason for that is that the compiler simply cannot know the address of the global variable. This is something that the task of the linker to populate these values. So the compiler essentially emits the proper relocations to help the linker to do its job. So what happens here is during the linking, the linker will fill up these values. And when these values are being added, then finally we will get the actual, the concrete address of the global variable. So this is basically the essence of relocations. Then relaxations are kind of similar. In this example, I just have a tail call of the foo function from the main function. And then it is being represented with two instructions, one add upper immediate to the program counter, and then there is a jump and link instruction. The point here is that we again have the relocation entries emitted, and there is an additional relocation entry, which is this relax entry, which is kind of a hint for the linker that, okay, you can even do some kind of optimizations, not just filling up the dummy values, but you can even, let's say, replace some of the instructions with more efficient instructions. So this is what exactly happens with this example. The linker realizes that the target address of the foo function is essentially very close to the jump instruction. So it can represent the call with a compressed jump instruction, which has just 2 bytes in size. And essentially this means we can save 6 bytes from the pair of instructions. They took up to 8 bytes. So this is very good. Now this is a table to summarize these jump relaxations. So of course we can use compressed jump instructions only if the target is very close. So if we want to address the whole address space, then we need to consider, we have to use a pair of instructions, and that's 8 bytes. Okay. So now this is the point where we can define the whole goal of the ZCMT extension, which is to encode the jumps of the whole address space jumps in just 2 bytes. So for that, we are going to introduce an instruction memory, a table instruction. A table in the instruction memory, and the address of this table is being held in a special purpose register. And we introduce 2 new instructions, 2 new compressed instructions. The jump table and the jump and link table instructions. The only difference is that the second is linking to the return address register. It's important to mention that this extension is part of a broader extension group, the ZC extension, which is targeting mostly code size optimizations. And this is an already ratified extension, so it's part of the RISC-V standard already. So let's see this in action. This is kind of a contrived example, but the point is that let's imagine that we have a kind of a state machine implemented in the main function. We have one state, and from that state we jump to the foo function. And then there is another state, and we again jump from that state to the foo function. And then let's imagine that this is a very large executable. So we have many, many functions in between the main function and the foo function. So the point is that the target address is really far away. So the compiler actually just simply maps these source lines to the jump and link instructions. What's important here is that the linker finally replaces these instructions with the compressed counterparts. And in this case, we will save 2 bytes for each of them. But you might wonder about the size of the table. So in this example, the table just contains one entry. And that entry is obviously the address of the foo function. Yeah, but this is in little endian, so this is why it might seem not the same for the first sight. So actually, we save 2 bytes with each compressed instruction, and the size of the table is 4 bytes. So finally, we saved 2 bytes. So the threshold of the repetition count, I would say, so when the address is the same, is at least 3. Okay, just to extend the previous table with this new instruction. Before I would say more about the implementation of this extension, I would like to say a few words about how the workflow is being handled or what's the workflow inside the linker. So first it collects the object files, then do all the classical relaxation, like the call relaxation I have presented before. And then comes the Zcmt relaxation. The reason for that is simple, because replacing a call with a compressed jump, that's the most straightforward thing to do, because then we don't need a table. Once Zcmt is done, then we will do all the relocations which are remaining, and then the final executable is ready. So the Zcmt implementation first is going to traverse through all of the relocations, the call and jump and link relocations, and we kind of calculate the benefit for each of the instructions that are connected to these relocations. This benefit is actually the number of bytes we can save. We can either save 2 or 6 bytes. So we store this benefit for each target symbol, I would say. Then we are going to sort the data we collected by the benefit, because obviously the size of the table is in the final executable is limited. So we want to get the most out of it. Then we write into the executable the table, and once that is done, we can simply replace the existing instructions with the compressed counterparts. And then we can essentially invalidate the processed relocations. So a few words about the results. So we measure very good benefits for large executables. For example, in case of free RTOS, the code size reduction can be 1.5%. And the results were even better for 64-bit executables. It can be even up to 4 or 5%. And now we are at ZCMI. So ZCMI is very similar to Zcmt in a sense. The idea is the same. It's just it's just extended to instructions. So to all of the instructions, not just jump instructions. So it's something that we would like to have smaller instructions to reference larger and frequently used instructions. It is essentially not a new idea. It has been introduced in 1997 by a white paper, or even before the Xerox auto computer have been using that. So the point is that we introduce a new instruction. This is the compressed instruction lookup table instruction. It has a fancy name. And essentially, as I said, we can compress almost all of the instructions, but there are some exemptions, like we cannot just compress a jump instruction. If you want to do that, there's the Zcmt extension. Also, it is not possible to compress instructions that are reading the value of the program counter. If you think about it, this is a fair restriction because it would be obvious, but not obvious, but ambiguous. What is the value of the program counter? So should it be? Actually, there is a two-phase. I would say there's a two-phased fetching of the instructions. First, we fetch the instruction lookup table instruction, and then we jump to the instruction table, and then we fetch the real instruction, which is going to be executed. So that's the value of the PC. So this is a draft extension. It hasn't been ratified yet. There's still ongoing work, and I have to highlight that the implementation of ZCMI is kind of similar to ZCMT in the linker. But there's a significant difference, is that we cannot just go through the relocations. We have to go through all the instructions. So this can be slow sometimes. You can see this in action. Actually, we can see that the number of bytes that we can save are really significant. But the measurements, the results we got are really promising. So in some cases, we can save more than 30%. In average, with the mbench benchmark, which is for embedded systems, in average we saved up to 4 or 5%. And we also experienced really good numbers with larger executables. Now you might wonder about the runtime performance, what happens with the runtime performance. So in case of that CMT, it's not really significant. So there is some code size reduction, but the score, the runtime score of the CoreMark benchmark isn't reduced that much, but it's not the case with ZCMI. We have a really good code size reduction, but the performance has been decreased like 39%. And so there is a solution to that, because we actually can specify a threshold to the instruction repetition count. So we can specify when to replace an instruction if that has been repeated more than a number in the whole executable. And this is actually the result that we get when we do the measurements in the function of this instruction threshold. So every application developer might be able to find a sweet spot for their own application. So if let's see, it's around 24 or 25 when you have a 10% code size reduction, and the trade-off is losing 10% of the performance. All right. I just wanted to quickly compare how RISC-V linker relaxations with LTO. So both of them are essentially whole program optimizations, but RISC-V linker relaxations are very architecture specific, on the contrary to LTO, which is not. And LTO is working on all kinds of optimizations, but these RISC-V linker relaxations are mostly code density optimizations. And obviously, they work with RISC-V machine code, in the contrary to LTO, which is working on LLVM IR. Okay, a few words about BOLD, because it has been really popular in this conference. So yes, it's a profile-guided performance optimization framework, and it's kind of a good idea, I would say, to use both together with RISC-V. It is also possible to do that. There have been many patches lately to support RISC-V with both. But this is not the case right now with our new extensions, because there is still work to do if we want to support both. One reason for that is so both reorders functions in order to get the maximum performance. And imagine if you have a compress jump instruction to a function which is really close to the call side, and both comes and then moves this further away. So the compress jump instruction will be no longer applicable. So this is the reason why both starts with unrelaxing the relaxations that had been done by the linker. So probably this is something that we should do with our new relaxation implementations. Other than that, at the end of its passes, after both, so both has many optimization passes, and after that it will relink the whole executable. And for that, it uses JIT-link. Why does it have to relink? Because, as I mentioned, it might reorder the functions. So essentially, it would be great if JIT-link was capable of handling these kind of new relaxations. But for that, probably the best would be to have a common library that can be used both in LLD and in JIT-link. Ultimately, if someone has, or if someone controls the whole build process and she wants to use bolt at the end, it's kind of not really meaningful to do the relaxations by the linker. Then bolt will unrelax those relaxations, and then at the end, bolt will use JIT-link to do these relaxations again. This is not so meaningful. So we think that it would be just the best if the relaxations would be done during the end of this process by JIT-link. A few words about the future work upstreaming. So currently, only the instructions for Zcmt are upstreamed. So we have a downstream implementation, and then if the community is interested, then we might be able to upstream it. Other than that, it's kind of a very interesting experiment to execute not just one instruction from the instruction table, but a sequence of them. This could have some significant performance gain. Actually, this is something that the Xerox Alto, similar to the Xerox Alto microcode, which has been invented in 1973. All right, and this is my summary slide, because I think this perfectly represents the simplicity and elegance of ZCMI. This is the iron-cast facade of America's first department store. So you have to remember this. Thank you very much.
Thank you.
Thank you. Do we have any questions? You make me walk all the way.
Hello, yeah, you probably mentioned this and I missed it, but for ZCMI, how common or how frequent must an instruction be to trigger the creation of a table entry?
Yeah.
And is that tweakable? Can you say I don't want to create entries for ads, but I do for other instructions?
Well, if you don't want to create entries, then I think you have to increase the threshold to a very large number. But actually, in our implementation, there's a parameter you can provide, and that's the threshold basically. So this was the table for it. So.
Thank you.
Any more questions? Yep.
Thanks for the talk, very interesting.
I just wanted to ask, you mentioned for the ZCMT that you have sorting of the benefits that each jump instruction gives. For the ZCMI, because there are a lot of more types of instructions, do you have some other heuristic, or do you just look at the benefits regardless of the type of the instruction, or is there something else?
Well, it's different from ZCMT, because in ZCMT you might either have 2 bytes or 6 bytes savings, but in case of ZCMI, let's consider on RV64 architecture you will save 2 bytes in every cases. So the count is what matters for the first place. Okay.
You see a fetching LLD from Vincent Group for ZCMT?
Yeah, probably I should
Do you
have
mind
said that.
repeating the question?
Yeah, so she said there's an ongoing patch about ZCMT. Yeah, I should have mentioned that it's not accepted yet, and I'm not sure. Yep.
Your implementation is along the same lines?
It's something that we have to check. So it's yeah, I think it's a bit different.
Yeah, of course.
Are you proposing ZCMI to RVI?
I think we have done it already. So
Given the performance implication, does it make sense to combine it with some sort of hot-cold splitting, so it's only done for the cold parts of the code?
well, yeah, I think it makes sense. But it's kind of always a trade-off. So yeah, it's really hard to answer. So it depends on the application. Yeah.
So imagine that introduces more longer, more expensive jumps. So it might not necessarily be a good trade-off. Any more questions? If not, thanks, Gábor, for the talk.
Thank you.